In this problem, we will continue our discussion of angle of twist in shafts that are connected to each other through a pair of gears. And in this case, we're looking for the angle of twist going from A to D. And we are going to spend quite a bit of time thinking about geometric compatibility to start off this problem. We will still get to the three pillars of geometric compatibility, equilibrium, and constitutive relationships, but for now we're just going to focus on geometric compatibility. And for this, we're going to imagine that this point D is fixed to a wall, such that the angle of D relative to some absolute ground would be equal to 0. So we've essentially replaced the boundary condition here with a reaction torque that would be equal to what you see with the m1g times a1. Okay, that torque that's being applied by the mass on this end. And this system is still in equilibrium. And for our intents and purposes of trying to figure out the angle of twist going from A to D, now we're going to say that this end is equal to, the rotation at this end is equal to 0, which makes it conceptually simpler. Let's think about the rotation of this large gear, phi of b. And here we're going to think about how phi of b might be rotating, or how the magnitude of phi of b compares to ground, which is now a fixed d. And for that imagination, we're just going to do the thought experiment of thinking that shaft CD has very low stiffness. So imagine it's something like a rubbery material. This means, assuming of course that these wheels are rigid and that there is no deformation between the teeth of the gears where they interact, that the angle of displacement phi b is completely dependent on how much twist there is in CD, and also something about these radii for the two gears. But without doing all the math yet, if CD is rubbery, that shaft CD is rubbery, you're going to see a lot of angle of twist for phi b. And so that means that if I'm thinking about, okay, what is the relative angle of twist from A here going all the way to D, I can think that this phi b relative to ground is going to capture somehow this angle of twist CD. And since I already know the angle of twist from A to B, that's what we calculated in question 3, we can then write the following equation to describe angle of twist A to D as being the angle of twist in the shaft AB plus whatever this angle of twist phi B is, and that phi B is going to be dependent on what's happening in CD. So if this shaft is very low in stiffness, then phi b would be small. I mean, if it's low in stiffness, phi b would be large. If it has a very high stiffness, then phi b would be small. And as I said a minute ago, we previously solved for phi of ab, and that expression is as follows, which you can see in the other video. Let's turn our attention to trying to figure out what is phi of b, because that's what we don't know. And for this, let's imagine that we place this gear, which we imagine as a wheel, on the ground. And we place this wheel gear on the ground, as you see here. And we rotate them both. So phi 2, phi 1, those would describe the angle of rotation for both of these gears. If this wheel is able to roll, then it will, I can think of it rolling some distance d2. I can think of this wheel as rolling some distance d1. If it's able to roll, I can describe the displacement, the linear displacement or linear travel, as being a function of the radius of the wheel and the angle of rotation, right? This is just thinking in terms of the circumference and how much of that circumference am I essentially rolling about as I move linearly. And phi is going to be in terms of units of radians. So we have now these two equations, and we also realize that they are connected, or they're touching each other. They're mated gears. And so the angle of rotation of these two gears, that's not the same. The radii are not the same. What is the same in terms of geometric compatibility, which is we're studying? The linear distance that these wheels would be mapping out. So we can say that d1 is equal to d2. Another way to think about this might be if I had some type of material, a sheet of material that I put between them and seeing, okay, I rotate them, how much does that material move and what's that distance that I go? Or maybe I could even think of putting these two wheels or gears on a cart, and as I translate the cart on a roadway or a sidewalk, I'm thinking that, oh, those two wheels are going to be rotating different amounts. If I have the small gear, right, it's going to have to rotate a lot of times versus the larger gear or the larger wheel would rotate less for a given amount of distance traveled by the cart. So we can write that phi 2 is equal to this ratio r1 over r2 times phi 1. Okay, that's just by doing some substitutions. And phi of b right here is equal to the phi 2. Okay, you see that for this gear. And phi 1 is equal to the angle of twist in the shaft CD. So now we can write that the angle of twist, which is what we're interested in solving, is going to be this angle of twist in AB plus now this ratio times the angle of twist in CD. So now our attention has to turn to what we don't know. We know radii, or the ratio of the radii, okay, that is given here. So this is R2 over R1, right? Here, and this is going to be flipped. So it's R1 over R2. And we got to figure out what 5CD is. So let's go ahead and let's get a new page out. And we're just copying what we wrote at the bottom of that last page, and also the expression that we solved for previously in question 3 for the angle of twist in shaft AB. Let's bring out our three pillars: equilibrium, geometric compatibility, and constitutive relationships. And if you're doing this problem, you might have more real estate with paper. So you could put 3 columns. You might end up wasting some paper because under one column you don't have much compared to the other two. But here I've kind of sorted things out, so of course they fit on the screen. Once again, when we're thinking about what's happening in a shaft, we can draw the shaft, and we're going to go from C to D. And this is very similar to what we did in question 3. Here, I'm going to put a TD on the end, on this rightish end. So I'm looking at the shaft, as you see here. And this TD, it's an external torque, and so I can pick a direction that makes sense. I don't necessarily have to follow a convention when I draw that torque. And that TD is going to be in that direction because you see there's an M1G and an A1 lever arm here that's pulling on it. There's going to be another torque, TC, acting in the opposite direction as TD. Okay, and so we know that TC and TD are going to be the same along this shaft. We take a slice along the shaft, as we see here, and we have our TD on the end, just like we had it here. And internally, it's probably a good idea to follow a convention that we've been, or the convention that we've been using, which is that if we take a slice and you have an open face, we're going to draw that internal torque, TCD, as being in the direction corresponding to a vector coming out of the open face. What is TD? Well, TD, I kind of alluded to it a second ago, or 2 or 3 or maybe more, that we have an M1G and we have an A1. So if we draw this lever arm and we give it its length A1, and we give the force M1G on this side, and we have now a reaction torque. So this is the torque from the shaft acting on the lever arm, TD, and of course they're the same, we can write out that TD is equal to M1G_A1. Let's turn our attention to geometric compatibility. And remember, we're focusing on what is the angle of twist in CD. So we're thinking pretty much just about the shaft at this point. Once again, we can write out the shaft, and we talked about this in question 3 about using a convention for angle of rotation that says that the angle of twist C to D is going to be equal to the angle of twist D to C. And we are, again, primarily concerned with the magnitude. We're not going to get too caught up in the direction here. And that's also in line with our thought experiment that we did earlier, that we had this phi b describing the angle of rotation of this large gear, and thinking, okay, if CD is squishy, it's going to have a lot of rotation. And the more phi b we have, the more phi A2D we're going to have, as described by here. So again, we're just thinking kind of the magnitude of this twist here. A constituent relationship that is helpful, and again, we did this in question 3, is TL over JG. It's a little bit different here, though, in that we have J1 describing the second moment of inertia, the polar moment of inertia, that for this shaft CD. We have that expression using C1, which we'll call the radius of this shaft, which is going to be half of the diameter of the shaft, so that'd be 0.55 centimeters. We can write out that the L that we're interested in is just this lower case L1, which is 9 centimeters. And the G is going to be this constituent relationship which we described in class of E over quantity 2 times 1 plus nu. This is the shear modulus. So we have our phi CD here, M1G A1 L1 over J1G, okay, just by plugging in M1G A1 here, and then we have L1 and J1 and G. We can now think, well, let's see before I show that. We have most of these terms, but what are we missing? A1, not L1, not J1, not G, not G. We're missing M1 because it's not given in the problem. Instead, we're given M2 on the other side. Now, this system is in equilibrium, so we can figure out essentially what, the reaction torque. Remember, we're kind of envisioning this as a fixed wall now. We can figure out what the torque would be here, or what the, and then if we know the lever arm, we can figure out what the M1G would be, that force as a contributing that torque. So we're going to go back to equilibrium, and we're going to think about the gears and how they are affecting the transfer of torque and the transfer of force, okay, also between the teeth of the gears. So let's look at the teeth of the gears. Here is my crude little drawing, okay, so the red one on the left, the purple one on the right, and we zoom in at the interface where the two gears meet, and we see something that looks like this, where there's some teeth, and let's just say that we have a pair of teeth touching each other. We could say, if this red gear is rotating counterclockwise, that it has upon it a force from the purple gear pushing it down. And we can say that the red gear, if it's rotating counterclockwise again, it's pushing up on a tooth on the purple gear. So these forces are equal and opposite to each other. Okay, so we have local equilibrium. And this is a very important point when you're dealing with gears, that we think of a equilibrium of force where they interface, not of an equilibrium of torque between the two. And yes, we have situations where you have equilibrium of torque when the torque's applied on a uniaxial member, as you see here with the shaft, but this is not that case. What do I and how do I rationalize that? Well, simply R2 is not the same as R1. Okay, R2 is larger because this gear is larger. So if I were to multiply F times R2 and I multiply F times R1, they are not going to be the same. So we don't have a conservation of torque here. We have a conservation of force where they meet. Now, with this conservation of force, we can still go about relating, okay, the torque on this end to this end. How do we do that? Well, let's draw kind of a 2D perspective of this problem where we're looking from point D, and we see if we look from point D onto it, we're going to have the B gear, and we're going to have the C gear. And so this is the one with the larger radius, and this is the one with the smaller radius. And I have a moment arm. Now I've drawn it a little differently because it would be complicated if I had it kind of behind here. So I've put it out to this side. That's essentially representing this lever arm with A2 and the mass M2. But I'm going to say that to keep that torque acting in the clockwise direction on the system, at least from this perspective, I'm going to move it to having a vertical force in the upward direction. And then I have an M1G, which is from here on the right side. And now I've drawn two forces. Now, these forces are actually in opposite direction, so the rotation would be opposite, but take a look at what's happening here. If there's a torque, right, on the left side that's causing us to go clockwise, then I need to have a force going vertical upward to create a counterclockwise torque on the system, okay? And so that means that that's why I've drawn the force here. So it's not the same, right? The rotation's the same, but it's still the same concept. And this is maybe one way to draw your forces. We have lengths of these moment arms, A2, A1, like that. And we'll call Z coming out of the page as our coordinate system of interest for taking care of the moments. So we write down R2 and R1, and we can write an equation for equilibrium about the center of this left gear, as we see here. So that's going to be FR2 minus M2GA2. Okay, FR2 would be in the counterclockwise direction, which is going to be positive. And if we do an equilibrium here about this point for the smaller gear, okay, we have FR1 is going to be positive, and minus M1GA1, which is going to be negative. Notice we did equilibrium about two different points of the system. So essentially, I could have broken this up where I have, if I drew a line through the system, kind of like this, right? That I've got one system on the left and one system on the right. And yeah, they're connected with this force F. And that's what we're going to do algebraically. We're going to go ahead and substitute in an F equals M1GA1 over R1 into this equation here. And so we get that M1GA1 R2 over R1 is equal to M2GA2. And we can finally define M1. M1 is going to be equal to M2GA2 times R1 divided by quantity A1 R2. So once we've defined our quantity, M1, we can go ahead and substitute it over here. And we get M2A2R1 over A1R2 times this GA1L1 over J1G, just like you see there. And now that I know phi CD, finally, I can write the final algebraic solution, which is that we have phi A to D equal to this phi A to B term here, plus, now look at this, we had an R1, R2, and we have an R1 over R2. So we have this quantity squared, and then we have m2 gl1 over j1g, right? We substituted m1. So there's no m1 written in this problem. It's all in terms of, or solution, it's all in terms of m2. This ratio squared between the diameters or the radii of the mating gears is very common in mechanics problems, whether you're solving for something that involves power, so you have torque omega, if you're solving, so like angular velocities or something, or you're solving for angle of twist. And note that one of the ratios comes from what we did previously with our geometric compatibility. Okay, it's actually, well, I don't want to go back there, but it was from going about and solving the phi CD, so primarily geometric compatibility. And the other ratio, R1 over R2, comes from equilibrium. Okay, so and that comes from this very important concept that the forces where they mate are conserved. Let's go ahead and solve this problem now. We have the equations, but we need a numeric answer. So for that, this is probably a pretty good problem to throw at Colab. And let's see, I'll probably have to move things around a little bit, but let's go ahead and for now, plug in some parameters that are of use to us. So we have M2, which is 11 kilograms, so let's change that. And I don't have an M1, right? And in fact, my final solution doesn't have an M1 either, because we've done some solving. Gravity is still that. A2 is equal to 6 centimeters, so we'll change that. Notice I also was able to eliminate the need to know what A1 is, all right, from my equation. So I have an A2, but I don't have an A1. A2 is going to be 6, right? We said that already. L2 is 10 centimeters. L1 is new. That's going to be 9 centimeters. And let's see, we have a C2, which is equal to 1 point, okay, it's the diameter, right? So it's half, so it's going to be 0.55 centimeters. C1 will be equal to the same, so just equal to C2. The elastic modulus, has it changed? Yes, 206 gigapascals, so very minor change. And the Poisson's ratio, 0.32, again, very minor change, probably not going to make a significant difference here. J2, okay, we need that, and we've solved for that previously. J1, we'll go ahead and we'll solve for that. And was it smart enough to get it right? Looks like it. Yeah, C1 to the 4th, and I've put in a C1. Okay, G, it's already got phi AB, great. Okay, so let's go ahead and let's define our phi A to D. That's what's interesting to us. So we have our phi, I can just write in phi A B again, plus we have this ratio R1 over R2. Okay, so I don't think I've put that in the problem yet. What do we have? We have R2 over R1, so that's the inverse of it. So we can do a couple things. We can call R1 R2, and we can say that's going to be 1 divided by 2.1. Okay, just like that. I don't really need parentheses. Okay, but so now I have an R1 R2, and I'm going to square that. And we have this quantity M2. So yes, I defined M2. We defined G times L1. Yes, defined. Good. And then this quantity J1 times G. Okay, that's defined as well. Okay, so we should be good there. So let's do a to D. Whoops, what am I doing? Oh, okay, great. It kind of knows what I want. I need to fix it a little bit, but A to D is equal to this. I'm going to do phi D. Yes, yes. Yeah, that should be good. All right, let's see if it works. And I guess before I do that, if you want to take a screenshot of what the code should look like, again, we have everything right here. And we'll go ahead and run it. And, well, that's a good sign that A to D is much larger than A to B, right? And so 1.45 degrees is what this comes out to be. Um, and you know, some of the principles that we covered here are an introduction or maybe a revisiting of what happens for the conservation of force between gears, what happens for the conservation of geometry or geometric compatibility between gears, and then relating the angles of twist that we have in these shafts to each other and coming up with an overall angle of twist. At any rate, I hope you've found this example useful in illustrating a few of these different concepts. Thank you.